Okay, so welcome to today's seminar. So today we are happy to have speaker Dr. Yen-Tsung from Penn State University. He's going to deliver an online talk, and his title is Linear Relation Among Polylogarithms at Point. Let's welcome him.
Okay, thanks for the introduction, and it's my great pleasure to present my current work with Harda here. So the topic I would like to present today is about the linear relations among Carlitz polylogarithms at algebraic points. And as I mentioned, yeah, this is joint work with Harada, and he's also one of the audience today. Okay, so here is today's outline. So I would like to begin with the motivation. The motivation comes from some classical, the result of classical polylogarism. Okay, and the second part I would like to present, I would like to state our main results and also some consequences. Okay, and in the end, if time is enough, then I would like to also give a sketch of the proof for our main result. Okay, so let's begin with the first part. Okay, so the first part is about the motivation. So let's consider this n be a positive integer. Okay, then we know that the n's polylogarithm is defined by the following power series. Okay, with the rational coefficient. Okay, so this is of this form. And we know that when n equals to 1, then it's related to the usual logarithm. Okay, and this power series induce a function on some region of inside the complex the set of complex numbers, and it converges for any z naught in C. Okay, with the absolute value strictly less than 1. Okay, then for the convenience of later use, we set this D to be the convergence domain for the polylogarithm. Okay, so it might be natural to ask. Okay, so we do have some analytic functions defined by the power series with rational coefficient. So given some algebraic non-zero algebraic number, okay, can we expect that the set of polylogarithm at this algebraic point can we expect that this set is a linearly independent set, okay, over rational numbers? Okay, so this
you consider different weight or fixed weight?
Sorry, the weight is different.
Different, yeah.
Yeah, the weight is different.
Alpha I is also in D.
Oh yeah, you're right. Thank you. Yes. So intersect with D. Yeah. Thank you. So yeah, the numbers are should lie in the convergence domain, and the weight varies. Okay, from 1 to n. So J can be from 1 to n. Okay. So we might interest in the linear relation among these values. So it's not hard to see that we are able to produce many relations among them. So we see that it's impossible to have a linear independent set over Q without any conditions. Okay, so it's not hard to see that some conditions are needed. Okay, so for example, we know that when we spatialize that n equal to 1, okay, this just equals to this one. Okay, and we know that this usual logarithm satisfying this relation. So combining with these two facts, we are able to produce linear relations among polylogarithms. Okay, so you can think this relation somehow comes from the multiplicative group. Okay. So from this kind of this relation, we can know that this question dates back to Baker's theorem for linear forms in logarithms. Okay, and after Baker, there are many results concerning this type of question. Okay, they study like logarithm or polylogarithm, their spatial values, the linear relation among their spatial values. Okay, so I cannot list all of the results here, but I would like to just present a current work, okay, about an explicit sufficient condition for linearly independent. Okay, so recently, an explicit sufficient conditions to this question has been established, and the result can be stated as follows. Okay, so this is the theorem in 2020. This established by David, Hirata Kono, and also Kawashima. Okay, in 2020, okay, they established an explicit sufficient condition, okay, on this algebraic point. Okay, so let's L over Q be a number field. Okay, and we just set this HL to be the veil height on L. Okay, so we just embed this L into the projective line. Okay, from what we just map alpha to 1 alpha, and we can just define the natural veil height on this L. Okay, and we also let this alpha 1 to alpha L are non-zero non-zero distinct numbers in L. Okay, and finally we also consider this beta just in non-zero numbers in L. Okay, then the result says that the set of the following NL plus 1 numbers 1 I over beta okay, these numbers are linearly independent over Q if the following conditions are satisfied. So they somehow define a quantity. Okay, they call this capital V alpha 1 to the alpha L, and also this related to beta. So this quantity is defined explicitly in the following way. this height of beta. Okay, so if this quantity is positive, okay, then these values are linearly independent over Q. Okay, so they produce this, they establish these sufficient conditions, and also their results can somehow cover some known result before. Okay, and for their results, so let's state in this way. Okay, so the advantage is that by using their result, they know that for given alpha 1 to the alpha L, you can always find a sufficiently large beta. Okay, so that this quantity is always positive. Okay, and if you just take a look on this term, okay, then you can see that this term is positive if the contribution of the height of beta almost entirely lie at the Archimedean place. Okay, so you just pick some beta sufficiently large with respect to the usual absolute value. Okay, then you can ensure this term is positive. And for the rest, you can, again, you just pick some large enough beta. Then you can always find some linear independent value. Okay, so the main purpose for today's talk, we are trying to study an analog of this question. Okay, so we are also interested in finding the some explicit sufficient conditions for the Carlitz polylogarithm at algebraic points. Okay, so this is the main purpose of our work. Okay, so far, is there any question? Are there any questions about the statement of this, our motivating theorem and our goal? Okay, so if there's no question, then let's move to the second part of our of today's talk. Okay, so let me start with the setup.
Sorry, I have
Yeah.
a small question.
Yeah, sure.
So in the theorem, so your number field is considered as a subfield of C first.
Yes.
In other words, you have chosen an embedding from L to C.
Sorry, yes, you're right. In this theory, we somehow fix an embedding first. I mean, we regard this L as a subfield of complex number. Yes.
Okay. And so the sufficient condition will imply that alpha I over beta has F value less than 1, or
let me see. I think that they somehow you can always pick sufficiently large beta, so that this absolute value is smaller than 1, so that it lies in the convergence domain of this polylogarithm.
Thank you.
Oh, yeah.
I wonder, since you consider only finitely many alpha I and beta, so why don't they state the theorem for it? Just Q bar. If you're given alpha I and beta, then of course they like some L.
Oh, so yes, you are right. Yeah, but I think that's because to state this result, they define this the veil height somehow depends on the number field. Sorry, let me see. Yeah, although it's somehow independent of the number field, but this height defined to be this one. So yeah, you're right, and certainly because we only concern finitely many algebraic numbers here. So yeah, it's somehow we can state in like they are in Q bar, and certainly they lies in a finite extension. Okay, so let me just complete. I think one reason is that they would like to, yeah, I just quote their result and they say it in this way. And I guess the reason is that they also want to use this kind of the highest function, and this somehow depends on the degree. But yeah, sorry, yeah, maybe next time I will just think how to present their result in a more appropriate way. But yeah, thanks for your.
Let's take in terms of fixed number field.
Sorry, can you say again?
They state their result based on
Uh-huh.
fixed number field. Yeah. It didn't say that. I mean, that's a question toward them. I just wonder.
Oh, okay, I see.
Their paper is stated for L. Fixed number field.
Yes. They for the statement of their result, they fix the number field.
It's okay. You.
Yeah, but to be honest, I don't really know the actual reason, and yeah, but yeah, thanks for your question and comment. Any other questions? Okay, if not, then let me just move to the second part. So I would like to just begin with the setup. Okay, so for the theory of the function field, the global function field, we start with this A to be the polynomial ring in variable theta with coefficient FQ. FQ is a finite field of Q elements, and this K is the rational function field. Okay, and we are able to define a norm on this field K. Okay, so we define in this way. So this kind of measuring the order at vanishing order at infinity. Okay, and once we have a non-Euclidean norm, we are able to take the completion, and this can be identified with this Laurent series field in variable 1 over theta. Okay, and finally we just take the completion of an algebraic closure of K infinity. Okay, and we know that we have this dictionary between number field and the global function field. Okay, so let's consider, let's define this L0 equals to 1, and we also define this Li to be this element in A. Okay, for each I bigger or equal to 1. Okay, then for any positive integer n, okay, we define the n's Carlitz and polylogarithm. Okay, abbreviates as CPL. This is defined as follows. Okay, so this is this Li n z defined in this way. Okay, so this is a power series with coefficient in K. Okay, so it's induced functions on the analog of complex numbers. So it's induced functions on C infinity. Okay, but it converges only on a small region, similar to the classical polylogarithm. So it converges for any z0. Okay, with the absolute value smaller than strictly less than this one. Okay, so similar to the classical setting, for convenience of later use, we define the convergence domain with this Dn, okay, and satisfying this condition. Okay, so again, we can just ask the same question in this function field setting. So again, given finitely many non-zero Algebraic numbers, and also they are distinct. Can we expect that these values are linearly independent over K? Okay, so since we know that this LIZ, this Carlitz polylogarithm, this is a FQ linear power series. So suppose that all these values are small enough, then we know that the FQ linear relation among all these alpha I imply the FQ linear relations among the polylogarithm. Okay, so this is probably the first kind of trivial relation in this direction. And I would like to also mention that, so similar to the classical case, so classical logarithm, there are some, you can produce relation just from kind of relations among the multiplicative group. So this phenomena, we also have this kind of phenomena in the function field setting. So I just want to introduce this relation, and I just want to mention this fact to convince you that there are really some relation among these spatial values. Okay, but I won't give a detailed explanation. So there are also some linear relations arising from the T module. Okay, so later I will just, to be more precise, what kind of T modules they are related. Okay, so these T modules are tensor powers. Okay, of the Carlitz module. Okay. But so far I just want to introduce a relation. So suppose Q equal to 3 and N equal to 2. Then somehow by using the structure of the T modules here, you can just view this kind of analog to the multiplicative group. Then we are able to produce this linear relation. Okay, so you can view this relation as the relation arising from the structure of T module. Okay, so I just introduced two types of linear relations. So you can see that it's not easy to. They are not always linearly independent. You can really have some linear relations among these the CPL at algebraic point. Okay, so our main result is trying to find. Sorry, could you say again?
One question.
Yeah,
Do
sure.
you expect that all the linear relations only generated by these two kinds.
Oh, I see. Yeah, it's a nice question. I think the answer.
Do you expect? I mean, you have worked on this question, so
Yeah, you're right. But I feel that's this kind of question somehow implicit answer in one of Professor Zhang's paper, because in his Cambridge Journal paper, he somehow shows that the linear relation among the polylogarithm, Carlitz polylogarithm at algebraic points, together with the periods, the power of pi tilde, all the linear relation just equals to the linear relation among the algebraic points on the T modules. So I think the answer, I believe the answer is yes. Yeah, all the linear relation among Carlitz polylogarithm at algebraic points always arising from the linear relation among the corresponding points on the T module. And I think also further, maybe using your result with Professor Zhang and also like result from Mishiba or Papanikolaou, we can also say something more on the algebraic relation. And yeah, I will also mention this part later. Does this answer your question?
yeah, fine.
Okay, thank you. Yeah, so our main result is the following explicit sufficient condition for the linear independence of Carlitz polylogarithm at algebraic point. Okay, so let's L over K be a finite extension. Okay, then for any positive integer n. Okay, and also this alpha 1 to the alpha L that's in here, but also intersect with the convergence domain of the Carlitz polylogarithm. Okay, thanks for the reminder from Professor Zhang. And we suppose that the following three conditions are satisfied. Okay, so the first one is kind of, we would like to exclude some kind of the trivial relation, okay, arising from this FQ linear relation. So we have to, at this, assume that they are all linear independent over FQ. Okay, and also we hope that their behavior at each place is kind of somehow restricted. Okay, so for every alpha I, the vanish order at place W, okay, where the W is the infinite place, okay, with places W of L, okay, lying above infinity, okay, should strictly greater than 0. Okay, and the third one is about the condition on finite place. Okay, not lying above the infinity. Okay, so suppose all these three conditions are satisfied. Okay, then we are able to show that all these values are linearly independent. Okay, and moreover, by using the result of Professor Zhang, we are able to kind of improve our statements to be more parallel with the classical result I just stated in the beginning. Okay, so suppose that this alpha I are in the intersection for L with D1. Okay, suppose this converges for any polylogarithm. Okay, then the NL plus 1 values Okay, 1 Lij alpha I. Okay, for they are linearly independent over K. Okay, I think, yeah, probably, yeah, over K bar. Okay, so I would like to explain this part. So I think what we have done, the most new part is the first half of the statement. Because for the later part, okay, starting from moreover, this is just the consequence of the result in this paper. Okay, because in this paper, suppose we define this vector space. Okay, span over K bar by using this one. And we define this V not K bar. Then the consequence of Professor Zhang's result is that the dimension of this one, of this vector space, just equals to the summation. Oh, sorry, I define this V bar here. And I also define this Vj to be, okay, span over coefficient within in K. Okay, this is more correct. Okay, then these two are equal. Okay, so somehow it says that all the linear relation descend to K bar linear relation descend to K linear relations, and also it shows that if the weight, okay, if J this index J varies, then there's no relation among different space. Okay, so the second half, the second part, starting from moreover, once we establish the first part of our result, the second part, this is just the consequence of results from Zhang. So it is not something new. I think the most probably interesting or new part is about the first part. We really find some explicit conditions, sufficient conditions, so that the Carlitz polylogarithm at algebraic points are linearly independent. Okay, so classically, the result by David and his co-authors, they somehow prove that linear independence result. So they are able to show that. Sorry, let me go back to the statement of their theorem. Okay, so from this result, find the sufficient condition for the linear independence among these values. Okay, so somehow they shows that the irrationality for linear combination of polylogarithm at algebraic points. Okay, so by using our result, we can also obtain the same consequence, but we can do further just by using some other strong result. Okay, obtained by, I think, firstly by Papanicolaou. Okay, he studied the case when n equals to 1. Okay, and later by Professor Zhang and Professor Jingyu in their advances paper, they studied the algebraic relation among the Carlitz polylogarithm at algebraic point, and also I think the refined statements was established by Professor Mishiba. Okay, so our by using this by using their result, our theorem, okay, implies that the transcendence degree of this field So that's the index is not divisible by q minus 1, and also not divisible by p. So here the p equals to the characteristic of f cubed. Okay, the transcendence degree for this one just equals to this quantity. Okay, this can be more general using the refined result by Professor Mishiba, but for simplicity, I just stay this version. Okay, so somehow it says that all these values are algebraically independent over k bar. Okay, and some of you may wonder, how about we join the Carlitz period? Because again, just for simplicity, I did not introduce this value. But if you just join this pi tilde, then you
So
just
what's the
consider.
condition on J? Q minus 1 does not divide J?
Oh, my bad. Yeah, you're right. So sorry. Yeah, q minus 1 did not divide J. Thank you. Yeah. So if you can also consider this field, but you also union the Carlitz period. The Carlitz period just analog of 2 pi I. Then you just plus 1, because this Carlitz period is also algebraic independent to this value. Okay, any question so far for the statements of the theorem and also the consequence? Because in the function field, they are already very there are many powerful tools developed by some other expert before. So yeah, I think the new part is just the first half of this statement. We establish the explicit sufficient condition. Okay, and the later consequence just applying other people's result. Okay, but the good thing is that we do have this analog of the classical statement, and we can even do stronger. We can also even answer the algebraic independence.
Excuse me, can you hear
sure.
me?
Yeah, sure.
In the first condition, can you replace FQ by FP?
Oh, it's a good question. Let me think. I didn't think this question very carefully, but I think I don't want to say something might be wrong. So sorry, I don't know now. I didn't think about this question, but I suppose we can. Yeah, yeah, you're right. We can really say something. I mean, yeah, I think we can really know the answer, whether we can replace or not. Maybe,
Okay,
but yeah. So far, I don't know. And yeah, I just don't want to say something may not correct. But yeah, thanks for your comment. Yes, I think it's probably also interesting to see if we can descend this condition to over FP. But yeah, so far we don't know. We don't know.
Okay.
Yeah. Thank you.
Thank you.
Okay, so let me just move to the third part of today's talk. So I would like to just briefly give a sketch of the proof. So first of all, I would like to introduce some notations. Let me just recall that this L over K, just a finite extension over L is just the finite extension over the rational function field K. Okay, and let's introduce a new symbol to this tau. You can view this from L to L. This is just the Frobenius Q map. Okay, and we can define the twisted binomial ring. So this is the twisted polynomial ring subject to the relation. Okay, tau alpha equals to q tau. Okay, for any alpha in L. Okay, so the reason why we subject to this relation is that we view the elements in this polynomial as FQ linear and the morphisms on L. Okay, so to be more precise, suppose we have an element, okay, in this L tau. So suppose this in this form, and how can we act elements in L? Okay, so this defined to be in this way. Okay, we just raise alpha to the some q's power. Okay, so this L tau can be realized as FQ linear endomorphisms on L. Okay, and this also reveals the reason why we should subject to this relation. Okay, because the multiplication there is kind of the composition of function. Okay, so let me just introduce. I just mentioned the T modules, so I would like to just give a very brief definition. I don't want to introduce the general T module, so let me just focus on a very specific one. Okay, so for any positive integer n, the nth tensor power, okay, of the Carlitz module. Okay, so this is just a very special case of the T module. Okay, so this is just a pair. Okay, I will use this border C, tensor n. This is just the pair. The underlying space is just the additive group, and together with this structure map. Okay, this brackets n. So this brackets n induce an FQ module structure on the nth copy of L. Okay, so where this n, the brackets n, okay, this is just a FQ algebra homomorphism from FQ to this matrix ring. Okay, so we just send this A to this symbol. Okay, so this is an FQ algebra homomorphism, and because this FQ algebra homomorphism, so it's uniquely determined by its image of T. Okay, and the image of T, we just assign this element to the image of T. Sorry, so the diagonal is 0. Sorry. Okay, and there's 1 here. And and we have 1 above the main diagonal. That is tau 0. Sorry, this is a bit messy, but anyway, yeah, just the matrix of this form. Main diagonal is theta, and the entry above main diagonal is 1. Okay, and in the left bottom corner, there's a tau here. Okay, so we just define this. The tensor power of the Carlitz module is just this pair. Okay, and by using this structure map, the brackets, okay, then we know that the nth copy of L is an FQ QT module, okay, via this the bracket. Okay, so this is just an example of the T module. So I would like to also introduce. So for A in the FQT, okay, if we are able to express this the bracket A of this form, okay, with alpha I. Oh, I shouldn't use alpha. Maybe let me just change to something else. So if this expressed as beta 0, the beta I, tau I, with all this coefficient in here, then we set partial bracket A defined to be this beta 0, the constant term. Okay, so what I want to introduce is for this T module, for the n tensor power of the Carlitz module, there exists a formal power series this log C, okay, of the form. So this is a power series with n variable. And I would like to use the column vector. Okay, so this is a power series without the constant term, and for the degree 1 term, it's just z1 to the zn. And also this is also again this is FQ linear. Okay. And with this pi in our matrix, square matrix with coefficient in K, okay, such that as a formal power series, the following functional equations is satisfied. Okay, for any A in FQT. Okay, so we already introduced the related object. Okay, now we are able to state the strategy of our proof. So as I mentioned, I just want to give the sketch of the first half of our theory, because the later part I'm kind of already give a briefly explanation, okay, by using the result of Professor Zhang. Okay, so sorry, the strategy for sketch of the proof. The step 1. Okay, so we already have these elements alpha 1 to alpha L. They are elements in L. Okay, we are able to define the corresponding array points on the Carlitz tensor powers. Okay, so let's consider this Vi in here. Then the step 1 is trying to show that we have this inequality. So let me just okay. So this the dimension is bigger or equal to the rank, okay, over FQT. And let's consider this FQT submodule generated by this point. Okay, and again, I runs from 1 to L. Okay, and the key ingredient in the proof of this step.
Will spend Vi over FQ.
Oh, my bad. Yes. Thank you. I just I just do not have enough space. But yeah, thank you so much. Yeah, it's over FQT. So I just want to say that the key ingredient for this proof is not that new. We kind of mimic the proof in the result of Professor Zhang in his 2016 paper. Okay, so the key idea is the first we apply this the result by Anderson and Tucker in their 1990s paper. Okay, they somehow show that the Carlitz polylogarithm really occurs in the last entry of the logarithm of the Carlitz tensor powers at this spatial point vi. Okay, so this is the first fact we use. Okay, and then we show that we are able to lift all the linear relation because every k linear relation among the Carlitz polylogarithm, okay, we are able to convert this to the a linear relation. Okay, so suppose we have some non-trivial linear relations among Carlitz polylogarithm. Then by using the result of Professor Jing Yu in using his less coordinates theorem, we are able to show that we are able to lift the linear relation among the less coordinates to be the FQT linear relations among the points. Okay, so we know that every linear relations among the polylogarithms can be lifted to FQT linear relation among points. So we just establish this inequality. Okay? And regarding the question asked by Professor Jing Yu in the very beginning, if we also join the pi tilde on the left hand side, then we do have the equality, but we should consider 1 plus the right hand side. So if we just revise our left hand side to be the polylogarithm, also join the nth power of pi tilde, then we really get the equality. Okay? But the quantity on the right hand side we should plus 1. Okay, so I think this somehow answered the question by Professor Jing Yu. So all the linear relation among polylogarithms together with period are always coming from the FQT linear relation on the T module. Okay, so this is our first step. We try to reduce our problem from study the value of analytic functions to something purely algebraic. So we want to study the algebraic relation. Sorry, no, not algebraic relation. FQT linear relation among some algebraic points on tensor power of the Carlitz module. Okay, so the step 2. Okay, in the step 2, we kind of using the theory of Anderson's DOT motive. We are trying to just rewrite every point on the T module in terms of some class, okay, in the quotient space of its associated DOT motive. Okay. But in conclusion, we try to show that the following statements are equivalent. So we're trying to show that the existence of the FQT relation among these points is equivalent to the existence of the solution of the following Frobenius difference equation. It's such that the following Frobenius difference equation hold. Okay, so let me just explain the notation very soon. Sorry, should be AL, alpha L. Okay, where this G twisted by 1 is equals to this one. When we express this in terms of the polynomial in T, okay, whenever our G is of this form. So we just raise the coefficient to Q's power. Okay, so this one lies in L, lies in L. Okay, so in the step 2, I think this part is more technical, but we just, in short, we just using the theory of Anderson DOT motive, and we try to analyze we'll just try to find the equivalent statement for having the linear relation, FQT linear relation among the points on the tensor powers of Carlitz module. Okay, so in the final step, as you can see, this to find the solution for this star, this is very restricted. If you just consider you kind of analyze the v-additive variation for each place to the equation star, then you will see that it's really difficult to find such the existence of such G and A1 to the AL. So in the step 3, we are trying to show that if all the elements alpha 1 to alpha L satisfying the sufficient condition we just state in the theorem, then there are no elements A1 to the AL in FQT, and also this G in LT. Okay, so they satisfy the difference equation star. Okay, so this is the sketch of our proof. Okay, firstly, we just try to using the results, some known results, try to convert our problem from this more analytically to more algebraically. Because after step 1, we just somehow transfer our problem from some analytical values to the FQ module relation, FQT linear relation among some points. Okay, and the step 2, we just try to find this equivalent to solve some Frobenius difference equation. Okay, and if we analyze this Frobenius difference equation carefully, then we can show that under some conditions, then there's no solution, which means there's no relation. Then from step 1, we can imply that we can know that these Carlitz polylogarithms are linearly independent. Okay, so I think I just stop here. Any questions?
So can you say further application in the v-additive case?
Oh, okay. Thank you. I also want to include in the talk, but I feel it's because I have only 1 hour. I worry I have to introduce too many notation. So let me go back to the classical case first. Okay, so first, you may think this condition is a bit strange, because if you just want to find something with large absolute value in the denominator, then you can just restrict your beta to something like in Z. Just you can pick beta just integer. But in their statement, because what they really prove is that you can also fix V naught a place, any place of L. And in the statement, you just change this to be V naught. Then they regard this value as the values in here. Then they are still linear independent. So their results, I feel their results are somehow also powerful, because their result is independent of the choices of the place. Although I only state the Archimedean place, but their result even works for the non-Archimedean place. So I feel this is something Nice. Okay.
So
So
you
this
mean
is the
their results also imply the linear independence of periodic Polylogarithms?
yes, yes. What I learned from their talk, because David gave a talk on online on I think from YouTube on the YouTube, and this is what he stated in his slide. And someone even asked during his talk, and he said yes. So I suppose this should be okay. Their result even works for PIDK. Okay, so let's back to the function field setting. So what I want to say is that our statements also work in the VIDK. I mean, we can pick any finite place, so we can regard this once we fix an embedding, then this can be realized as a power series here. So this also induce some functions on CV. V is just a finite place. Okay, and so certainly we have to change the condition here, the convergence condition. Okay, but once we adjust this part, then the condition we stay here still valid also in the V-adic setting. So this is quite parallel to the classical setting, because classical setting the result also works for the p-adic setting, the p-adic p-adic polylogarithm, and in our result also work for the V-adic setting. Okay, so we can also know the linear independence among V-adic polylogarithm. But there's one part is missing, because for the algebraic independence, this only works for the infinite-adic setting. Okay, so for the V-adic setting, what we have is we only have something above here. Okay, so I think this is very nice question, and I also want to include the V-adic in the talk, but I feel it's probably takes more time to explain some notation. So yeah, so I did not mention, but yeah, thanks for your question and comment. I think yes, we can have something for the V-adic value.
Are there any questions or comments?
Can I ask a question?
Yeah, sure.
Hi, this is Furusho. Nice to meet you.
Oh yeah.
Thank you very much for
Thank
the talk.
you, yeah.
So I have a question.
Yeah,
So,
thanks.
so in your nice theorem, so you assume three assumptions, yeah? And so, so I don't see exactly. So in which place the second condition, second assumption, the third assumption, where the two assumptions are used?
Oh, okay. Thank you. So yeah, you may wonder why the places above infinity is somehow spatial than the finite place.
Yeah.
Yes. Because in the step 2, we somehow we can kind of convert our question to solving the Frobenius difference equation.
Yeah.
And
Yes.
in this very specific Frobenius difference equation, the only constant occurs is theta. And so I think how should I say, for this theta, we only have this one, I guess. There's a 0 if lying above. Sorry. Yes, because theta satisfying this condition. So to study this very specific Frobenius difference equation, because the only constant different than alpha 1 to alpha L, or I mean the only constant appears in this equation is theta, and theta satisfying this property. So this is why we should somehow distinguish the infinite place and finite place.
So is it possible to exclude these two assumptions by using my method of analytical continuation using Artin-Schreier?
Oh, I see, I see. I think this
Or maybe
I didn't think this question so we didn't think this question yet. And
so there's a branches, but the branches is just a power of pi, right? My method,
yeah,
in
you're right.
context. So even it looks true without assuming the condition. I'm hoping.
Oh, okay. I
Maybe
see. I
I'm
see. Yeah,
wrong.
I think it's no. I think it's probably natural to ask because
Mm.
although our result works for like arbitrary places, but the condition is still the same. So yeah, the places lying above infinity is something. Yeah, you may wonder whether we can kind of remove or kind of improve this part.
Yeah, the two assumption looks quite technical, so that's why I
you're
like
right.
to exclude it
You're right.
using the methodology condition. I don't know, so that's why I'm asking.
Okay, I see. Yeah, I think it's good question, but we didn't think about this so far. So yeah, we will try to find out if it's possible to to kind of improve this technical condition.
Okay. Thank you very much.
Thank you. Yeah, thank you for your question.
I'll be in Taiwan tomorrow.
Oh, I said I just hear from Vicky. Yeah.
Any further questions, comments? So in the VRD application, you use VRD. You use SOEs.
Oh, yes, you're right. So for the Leviatic case, some results are missing, but fortunately, in the step 1, the result of Anderson-Thakur still okay. And I think the most important part is the result of Professor Jing Yu in his theorem. This less coordinate theorem also valid in the Leviatic setting. So yeah, so this is the reason why we are able to prove the result. Because if we have the step 1 in the Leviatic setting, then we can again reduce our problem to the algebraic point again. But by algebraic points on the Carlitz tensor powers, then yeah, then this condition is somehow independent of the choices of the places because we just study the algebraic point. So this is something nice. Yeah. So yeah, thank you. So yeah, so yeah, we have the VIT setting for Anderson-Thakur and also Professor Jing Yu's theorem. So we can prove the VIT setting.
But in the classical case,
yes.
Kind of transcendence result did I use?
Oh, you mean the strategy of their result?
Yes.
Oh, let me think.
They show the linear independence of the periodic polylogarithm. Oh, over Q, not over Q,
not over Q1.
Okay.
Yeah.
Okay.
I if I remember correctly, they can somehow extend this Q to something probably slightly larger, but I'm not so sure. So I just stay this one. I have to check their result. I'm not so familiar with their method, but they say they are using this kind of approximation. I'm not so sure if this is something, probably some methods from the transcendence theory or Diophantine approximation, but yeah, I don't know much about their strategy, about their method, but yeah, their result seems quite nice from what I learned from his talk. Yeah, so
So any questions or comments? If there are no further questions, let's thank Yen-Tsung again.
yeah, thank you.